If your chemistry students know all about metallic bonding, you know, those bonds that hold metallic atoms together because of those valence electrons that are mobile throughout the metal. If your students are all caught up on ionic bonding between a metallic atom and a nonmetallic atom as a result of the transfer of valence electrons from the metal to the nonmetal, and if your students are all caught up on covalent bonding, you know, those bonds that hold the atoms, for example, within water together, like oxygen and the two hydrogens, because they're sharing valence electrons. And it is time for you to focus on intermolecular forces, either because you haven't taught them yet or you're ready for review, then this video is for you. Refresher on intermolecular forces. We see here a test tube with liquid nitrogen. You cool it so much, bring those gas molecules together, thanks to intermolecular forces, and you've turned that nitrogen into a liquid. Or carbon dioxide, also normally a gas. You cool it enough, bring it together, and you turn it into dry ice. Quick to sublime, but still. And thirdly, and this was particularly important during the COVID pandemic, when we desperately needed more oxygen tanks. Well, how can we get that liquid oxygen? Because oxygen can come closer together as a result of these intermolecular forces. The key scientist that came up with these intermolecular forces that helped us in our understanding of states of matter was Johannes Diederik van der Waals. He received a Nobel Prize in 1910, a Nobel Prize in Physics, and he did his research at Leiden University, where I went to school decades ago. So in this video, I would like to share with you the lab that I do with my students to either review or help them understand intermolecular forces. I call it the Volatility Lab. Before I'm ready to show you the demonstration that my student gives here in this video, let me take you to the handouts, the keys that I have, and also sample student data. All these materials you can find in the description below. You just need to click on the link and it'll be yours at no charge to you. You're welcome. We've reached here the handout that the students receive. Let's zoom right in on the purpose. So the purpose of this lab is for students to come to an understanding of the relationship between volatility and intermolecular forces, or van der Waals forces. And what they're going to learn is that the stronger the intermolecular force, well, the less volatile the substance is. We're going to be working with 3 substances at a very much a microscale level, namely methanol, pentane, and rubbing alcohol, or isopropyl alcohol, or propanol. Let's check out the setup. You see here my student pouring some hot water, lukewarm, and some room temp water into a little petri dish and covering it with a watch glass. Now he's going to add hopefully one, I think he's adding 2 drops of methanol on each watch glass. And then it's literally waiting for that drop to vanish. My other student is hitting the lap button to stop when that first warm watch glass caused the 1 drop of methanol to evaporate. It took a little bit longer for the one that was colder. You would do the exact same thing with the other 2 substances, namely the pentane. This one is very volatile and a little bit difficult to get just 1 drop on the watch glass. And they will also do it with isopropyl alcohol, which might seem to take an excruciatingly long time, possibly 100 to 200 seconds. This particular document shows you the Google Sheets that will be given to the students. It's very empty. They have to create their own table for either their group, or if they prefer, if you maybe have very small lab groups, they can figure it out individually. But the nice thing is, dependent on how much time you have at hand, I actually encourage my students in a given lab group, whether it's a smaller or a bigger lab group, to pool their data and get an actual class average. This is the key Google Sheets that shows you the actual data that I've gotten with one of my chemistry classes. And you can clearly see here that it took pentane a very short amount of time, especially the warm pentane, to evaporate, that 1, maybe 2 drops. It took methanol a little bit longer, and isopropyl alcohol took the longest to evaporate. And you could see here the time in seconds, and here it's shown as a bar graph. Students then paste that chart right into their Google Doc through a hyperlink, okay? And then they will actually look at the structure of each of the 3 different substances. So I actually stole the images from online. Shh. They are actually supposed to draw it using the drawing tool within Google Docs, or if you prefer the paper method, you can just go colored pencil or pen and paper. Besides the structure, they will also calculate the molar mass or gram formula mass of the 3 different substances and take a look at the chemical formula and see if there's a functional group present within the given substance. Methanol obviously has a hydroxyl group. Pentane is just a simple hydrocarbon. And isopropyl alcohol or rubbing alcohol also has the hydroxyl group, but it's a longer molecule. Next, this lab involves about 8 discussion questions that help them get to a claim evidence reasoning statement. So these are some very important questions. You're seeing here already the answers to these questions, and they're also incorporating in their answer the data that they've actually gotten. Because they only tested methanol and isopropyl alcohol, one of these questions is really key because it allows them to make a prediction. What would happen if we tested ethanol? Ethanol being smaller than rubbing alcohol, but larger than methanol. What would be the predicted volatility of this substance that they did not test? They end the lab by completing a claim evidence reasoning statement by answering the question, what is the relationship between volatility and intermolecular forces? So upon completion of this lab, I really hope that your students, as did mine, have a better understanding or re-understanding of intermolecular forces. I highly recommend purchasing these metallic and magnetic water molecules. They come from Flinn Scientific. No, they did not sponsor this video. They are not cheap, but I'll tell you, they maintain their integrity and they don't get as dusty as the styrofoam or paper models that you may have in your classroom. And you can even create a hexagon. The eye structure is shown right here. This is the actual Flinn Scientific site where you can find this water kit. The water kit also comes with a couple of magnets that can represent sodium and chloride. I love these. You can even order a separate model that gives you more of these sodium and chloride magnets, not necessarily reflecting the intermolecular forces that we talked about in this video, but certainly emphasizing other types of bonding, such as the ionic bonding that's modeled here. This website shows you where you can find on Flinn Scientific the sodium chloride crystal lattice model. So the power of this volatility lab is you really bring all the different bonds together and now focus on those intermolecular forces. We have covered here the next generation science standards and the New York Science learning standards, HSPS1 on matter and its interactions. Obviously, intermolecular forces are very much related to volatility. They are very much related to bonding in general. So make sure you check out my other bonding videos where I focus on exothermic reactions, how you can model these reactions with your students, either using tactile components or a computer simulation. And stay tuned for a video that I'm about to record on endothermic reactions and how you can model those using a similar tactile setup en computer simulation. Bedankt voor het kijken. Thank you for watching. And tot ziens. See you in the next video.